Welcome to this deep dive explainer. We're going to cut right to the chase today. We are breaking down a technical analysis that is going to completely shatter how we traditionally think about computing, physics, and even the very concept of simulation. If you've ever felt frustrated by endless algorithmic lag, massive power consumption, or AI hallucination, you are going to love this. We're going to unpack a revolutionary idea. Are we just calculating the world, or can we let hardware literally become the world itself? Let's dive in.
So here's a thought that hits right at the core of our blind spots. Your pendulum never swings the way you think it does. In physics class, the equation for a simple pendulum is elegant. It's just length and gravity. But in reality, if it's in water, there's resistance. In the air, you have molecular collisions. The moment you add a flexible string or friction at the pivot, the movement becomes infinitely complex. And this begs the question, for the past few decades, when we fired up supercomputers to simulate these phenomena, are we actually solving physics, or are we just running away from it?
Section 1. The fundamental limits of digital. This exposes the massive trap of modern computing. To get a digital computer to understand the real world, we've fallen into a vicious cycle of simplifying first and solving later. Think about it. If you want to run a collision simulation with 280,000 degrees of freedom, 20 milliseconds of real-time action might take 40 hours to compute. We're burning insane amounts of computing power just on endless numerical corrections. A digital pendulum relies on discrete steps, delays, and complex solvers. But an analog pendulum, the concept is totally mind-blowing. Instead of spending massive resources trying to simulate continuous physics, you just replace the pendulum bob with a capacitor. You swap gravity for voltage and resistance for conductance. You plug it in and you don't calculate the trajectory at all. The physical hardware literally becomes the pendulum, bound by the exact same differential equations. No algorithm tweaks needed, just Ohm's law doing its thing. Section 2, EV, control, or physics. Let's transition from a simple pendulum to a wildly complex, multivariable real-world system, electric vehicles. When an EV hits the brakes, is it calculating or is it just responding? To really grasp how bloated the traditional digital approach is, just look at how we currently handle EV braking. Step 1. Sensors sample the data hundreds of times a second. Step 2. The ECU calculates the slip ratio. Step 3. The algorithm decides the braking pressure. Step 4. The controller finally adjusts the motor torque, and you still have to wait for the battery management system to sign off. It's agonizingly slow. It's a bloated, fragmented nightmare. In the digital world, these are 4 completely separate modules. We are taking a beautifully continuous physical process and chopping it up into discrete, lag-filled fragments. Section 3. Admittance replaces algorithms. And this is where the paradigm completely shifts. We have to stop treating an EV as a digital control problem. It's not. We need to treat it as the natural behavior of a continuous physical system. Motor drive, wheel momentum, braking, kinetic recovery. In the analog world, these aren't isolated modules anymore. They are different terminals of the exact same differential equation. Now, you might be thinking, doesn't kinetic energy recovery need super precise algorithmic current control? Nope. Current control doesn't need a precise algorithm. It only needs the correct admittance matching. The analog memory of the system already stores the admittance values for the recovery path. When braking conditions change, the current automatically follows, because current is literally just the natural response of voltage over admittance. You don't have to control it. You just let the circuit know where to flow, and the law of conservation of power balances it all out instantly. This quote right here captures the core philosophy of this whole analysis. They are making a digital twin. We are making an analog native. Digital systems need massive GPUs just to drive a simulation within their clock limits. But analog hardware, the moment you power it on, it instantly becomes the simulated object. A digital chip is bottlenecked by PCIe bandwidth and clock speeds, but analog computation is bottlenecked only by the speed of light. When an AI that approximates physics goes up against hardware that actually is physics, there's absolutely no contest. Section 4. Why no car or chip needed? Now, facing this level of disruption, you're going to hear a lot of skeptics. They'll say, if this is so amazing, why not put it on a physical chip or test it in a real car right now? Well, we haven't tested it on a real car because we absolutely don't need to. It's a bold statement, but it's true. Real car validation is engineering. We are building physical cognition. When you understand that an OTC array shares the exact same differential equations as the vehicle's physical dynamics, testing on a real car just becomes an engineering task of printing a PCB. We are solving fundamental physical laws, and physics doesn't need to be re-verified. It just works. And the performance gap we're talking about, it is a massive 3 to 6 orders of magnitude. For anyone arguing that digital can handle real-time demands just fine, this is the ultimate reality check. The absolute best a digital system can do is approach real-time within the limits of its clock cycles. Analog, on the other hand, responds at physical speed. Digital is chained down by sampling rates and loop delays. Analog is only constrained by the speed of light and RC time constants. A gap of 3 to 6 orders of magnitude isn't just a tech upgrade. That is a civilization-level leap. So why are physical silicon chips treated as secondary here? Because the heavy lifting is already mathematically defined by the CSDL v1.4 framework. This means that manufacturing the chip is basically just like operating a printing press. Any standard 40-nanometer process can easily replicate it. We aren't just selling chips. We are defining an entirely new coordinate system for analog computing. Physics cannot be plagiarized. It can only be verified. Section 5. A civilization-level leap. Now that we've defined this entirely new computational coordinate system, this tech goes way beyond just electric cars. Let's zoom out from physical mechanics to the grandest challenge of our time, artificial intelligence and cognition itself. Analog hardware mirrors biological brains with shocking perfection. Look at digital AI. It relies on feeding terabytes of data, discrete epochs, and backpropagation. But a biological brain? It has no clocks, no discrete sampling. It solely relies on continuous time-constrained relaxation. In an analog circuit, the node voltage maps directly to a neuron's continuous membrane potential. The fixed admittance matrix perfectly mirrors synaptic weights, entirely bypassing backpropagation. And the variational relaxation of the circuit naturally finding its steady state, that is exactly the cognitive convergence of thinking. This framework gives birth to true L5 analog AI. It's a processor with no discrete sampling, no clocks, and no epochs, just continuous physical relaxation. And here's the real game changer. When digital AI encounters noise, it hallucinates, crashes, or gets stuck in brute force loops. But when L5 analog AI faces unknown noise or conflicts, it does what a biological organism does under immense stress. It physically slows down its relaxation to ensure absolutely zero error decisions. It might take its time, but it does not hallucinate. The answer is always physically correct. This isn't just about building a faster chip. It is a profound philosophical pivot. If thinking is literally just a physical system undergoing relaxation to find a steady state, do we even need the Turing test anymore? When a digital AI model overfits, is it learning, or is it just memorizing symbols? But when an analog circuit undergoes physical relaxation, is it calculating, or is it physically existing as the decision itself? It's a question that completely redefines the future of artificial intelligence, and the answer might have been hiding in Ohm's law all along. Thanks so much for joining me on this explainer, and I'll catch you in the next one.